Thanks a lot for the introduction, and thank you so much for having me. So today I'm going to share my recent work on theoretical advances in diffusion models. And if you have any questions throughout the process, please feel free to put them in the Q&A box. Yeah, okay, so let's get started. So the outline for today, I'll start the talk with a really brief introduction to what is diffusion model. So this is just like a special example of deep generative model. And in the first part of the talk, I'll talk about a trick to accelerate diffusion model. This part is based on drawing work with Yuchen and Yuchen, both from UPenn. And in the second part, I'll talk about posterior sampling algorithms that is motivated by the structure of diffusion model. And this part is based on drawing work with Andrea Monte Carlo from Stanford University. All right. So to start, diffusion model, this is a generative model. And to start and to make sure everyone's on the same page, let me just start with a quick introduction to what is a generative model. So suppose we have a target distribution mu. So this is the distribution we want to sample from. And then we also have some training data coming from this distribution mu. So here, for example, we have images of cat faces. And then we'll just pass this training data into a generative model training procedure. And hopefully this will enable us to build a generative model that is capable of drawing samples from the target distribution mu. And here, one caveat is that we want this generative model to not directly output the samples from the target training dataset. Instead, we wanted to generate new unseen samples that kind of fit in well into the training dataset. So for generative model, there are many prominent examples. For example, we have the generative adversarial network, we have the variational autoencoder, and we also have the diffusion model that we are going to talk about today. So diffusion model, just to remind you a bit, is the backbone behind many successful machine learning applications like DALI, Sora, AlphaFold, and Imagery. So what is diffusion model? On a high level diffusion model, it consists of two processes. There is a forward process where we start with sample from the target distribution. So here we have like an image of a tree. And at every diffusion model iteration, we are going to add a small amount of noise into this image until we get random bits. So that's the forward process. It's pretty standard. There's nothing magical about it. The magic lies in the reverse process where we start with random bits. And at every diffusion model iteration, we are going to apply some sort of denoising procedure until we get image from the target distribution. So if you look at this process, you might ask, like, how is this possible? Like, how can we generate a tree out of pure noise? So the magic lies in the denoising procedure where we call certain functions that are trained to capture some property of the forward process. And also, I want to emphasize that to generate one sample using the diffusion model, we only implement the reverse process, and the forward process is mostly for theoretical understanding as well as for model training. Okay, so reverse process is a very important component of the diffusion model. And one specific instantiation of the diffusion model reverse process is the denoising diffusion probabilistic model, or for short, DDPM. So how this DPM works is that it attacks the i's diffusion model iteration with a time index ti that is strictly increasing for I from 0 to k. And also we denote by yi the iterate after the i's diffusion model iteration is completed. And from the previous slide, we know that y naught is just pure noise. And after all the diffusion model iterations completed, hopefully this diffusion model will output a new sample yk that is coming from the target distribution. And to put things down a bit more formally, at the I diffusion model iteration, we define the step size delta I to be ti plus 1 minus ti. And we also set alpha I to be exponential of minus 2 delta I. And this DDPM, as we discussed before, is initialized at a random distribution. So here we take a standard Gaussian distribution. And at the I diffusion model iteration, it will update yi plus 1 as a linear combination of yi, a denoising function si applied to yi, and a standard Gaussian random vector gi. So here you can see that the linear coefficients here depend only on alpha I, which is basically defined as above. And to tell you a little bit more about this denoising function, recall that the target distribution is new. So this denoising function Si, you can roughly speaking think of it as an approximation to the gradient of log Qi. So this Qi is defined here. So this is like a Gaussian convoluted version of the target distribution with the convolution coefficients Bi and Ci being explicit functions of the time index Ti. So this Qi is just like a Gaussian convolution. And this gradient of log Qi, we call it the score function of the diffusion model. So this is like a very important component of the diffusion model. But of course, this target distribution mu is a distribution that we do not know in practice. So this means that the score function is also not known. And in practice, people usually use a trick called score matching to estimate the score function, which usually involves training massive neural network using a large amount of data. To tell you a little bit more about this score function estimation procedure, let me first simplify the expression of this score function. So using 3D's formula, we can actually see that this score function, it can be expressed as some sort of conditional expectation. So to be specific, this is the conditional expectation of Z, conditioning on Bix naught plus Ciz equals X. So here, Bici are the coefficients that appear up here, and X naught Z are two random vectors. They are independent, with X naught distributed according to the target distribution, and Z is a standard Gaussian random vector. So this expression is pretty straightforward, and actually it motivates us to estimate a score function by solving a L2 empirical risk minimization problem. To tell you a little bit more detail, so suppose we have like a bunch of training data x1 to xn, that's IID coming from a target distribution mu, and then we'll add noise to this, or we'll manually add noise to this training data set to obtain x1 bar to xn bar with xk bar. Here I should use k instead of I, with xk bar being bi xk plus ci zk. And here, z1 through zn are IID from a standard Gaussian distribution. Okay, so now we get this noise version of this training data set, x1 bar to xn bar. And then we'll use this x bar to construct an estimator to predict the noise that's previously added to the training data set Z. So basically, we predict Z using x bar, and the process involves some L2 empirical risk minimization. Okay, so as I discussed before, this procedure usually involves training massive neural networks, so it's very complicated. And in this work, we are going to propose to avoid the analyzing the complexity of massive neural network training by assuming that we have access to a pretty good estimate of the score function. That is to say, we will assume that we have a good quality pre-trained denoising networks. So this assumption, first, it allows us to focus on other aspects of the diffusion model beyond the neural network training. And also, this is the assumption that's been adopted in a lot of the previous diffusion model theory papers. Okay, so that's the roughly the procedure of diffusion model. And so diffusion model is very powerful, but on the other hand, if we talk about sampling this diffusion model, then this procedure is also very slow. And for example, if we want to draw one sample using the DDPM, then this procedure involves hundreds to thousands of sequential callings of massive neural network. And to give you more evidence, I'm taking this code from Somo and Ermo. It says that to generate 50,000 images of size 32 by 32 on the same GPU, GAN requires less than a minute. However, DDPM requires more than 20 hours, suggesting that for the large-scale application of diffusion model, acceleration is really essential. Okay, so this leads to the first part of my talk. So this part, I'm going to discuss a training-free acceleration method for diffusion model based on joint work with Yuchen and Yuchen. So we are not the first one to study acceleration for diffusion model. There are many existing acceleration methods for diffusion model. So roughly speaking, they can be categorized into two categories. In the first category, we have training-based acceleration method. And in this category, we have model distillation, sample trajectory learning, as well as consistency models. So by its name, you can see that to implement a training-based acceleration, we first take some pre-trained denoising networks, and then we incorporate some extra training to build a new sampler, and then we proceed to sampling. So the training-based acceleration methods are very powerful, but on the other hand, they could be computationally very expensive because of the extra training step. This is especially the case if the model scale or the problem scale is very large. And the second class of acceleration method is training-free acceleration method. So from its name, you can see that this class of acceleration method involves just modifying the original diffusion model without introducing any additional training. So we just take the pre-trained denoising network, we apply some tricks without introducing any extra training, and then we proceed to sampling. So this training-free acceleration method is good for obvious reasons because it's computationally efficient. It doesn't involve any extra training. And in this talk, we are going to focus on this class of training-free acceleration method. So the question we are going to ask today is, can we design a training-free acceleration method for diffusion model that probably converges to the target distribution? Okay, and then I'm just going to state what is the proposed accelerated sampler. So recall that this is the updating formula for the DDPM. Basically, DDPM as diffusion model iteration, it updates yi plus 1 as a function of yi, si of yi, and gi. So our modification is actually pretty simple. It's just like add an additional random term into the input of the denoising network. So before we have si of yi, and now we have si of yi plus xi. So here, this xi I, it is a Gaussian random vector that is correlated with the random vector gi that's initially presented in the diffusion model. And to be specific, the covariance or the correlation is characterized by a function that depends only on delta I, and it depends on these three functions f1 to f3. So for the sake of simplicity, I'm not going to tell you what's the specific definition of these f1 to f3, but these are functions that are explicitly given in a paper, and you can find it in the paper. Okay. And just to comment a bit on the acceleration trick that we propose, first of all, you can see that it's very simple to implement. Essentially, we just add an additional random term to the input of the neural network, and we don't need to train an additional neural network. And also it's training free. It doesn't require any extra training. And also you can see that it wraps around any pre-trained denoising network. So essentially we just take the existing denoising network from existing diffusion model project, and we apply our modification, and then we can proceed to sampling. So these are the good points about this, our accelerated sampler. And then you might ask, like, what is the intuition for this design? Like, why we add an additional random term to the input of the neural network? So the intuition is that if I look at this diffusion model, then there is an underlying process that maps a random noise to sample from the target distribution. So this is a continuous time process. And if you look at the formula, this is defined by a stochastic differential equation that's given up here. And you'll see that a lot of the diffusion model-based samplers is just designed based on the idea of tracking this stochastic differential equation. So for example, DDPM, you can think of it as providing a first-order approximation to this continuous time process. And our acceleration method, by incorporating this additional random term, you can think of it as providing higher-order approximation to the same process. And okay, so that's the intuition for our design. And finally, I'm going to give you some guarantee of our method by giving you both a theoretical guarantee and some numerical evidence suggesting that our method can work well in practice. So here, I'll first give you the theoretical guarantee. So in this theorem, we say that if we assume the score function estimates are accurate in the sense of L2, as we discussed previously, then to ensure that the output distribution and the target distribution are epsilon square close in Carrel divergence, then the proposed sampler requires of order d to the power of 3/2 over epsilon number of function evaluations. So here, just to comment a bit on our theoretical result, the first thing is that we do get some improvement over the previous acceleration method. So if you look at one previous acceleration method proposed by Li et al., then their acceleration method requires of order d to the power of 3 over epsilon number of function evaluations to obtain the same accuracy, epsilon squared accuracy in KL divergence. And the second thing is the proof. To prove this theorem, we essentially apply a theorem called the Kirsanov theorem in probability theory to bound the KL divergence between the output distribution and the target distribution. So that's the theorem guarantee for our acceleration method. Okay. And finally, I'm going to conclude this part with a numerical experiment. So for the numerical experiment, I'm going to focus on the task of image generation. So this is a task that diffusion model has found a lot of applications. So for benchmarking algorithms, I'm going to use both DDPM and the acceleration method proposed by Li et al. And I'm not going to train my own score network. Instead, I'll take the pre-trained score network from this paper, Nico and Darivo. But for your experiment, you can take any score network from any existing diffusion model projects, or you can train your own score network. And as for the number of function evaluations, I assume it is between 10 and 100. And for each of the settings that I mentioned here, I'm going to generate 10,000 samples and calculate what is the feed value for the samples that we generate. So this feed value, roughly speaking, you can think of it as an estimate of the image quality or a measure of the image quality. With the lower the feed value, the better the image quality. Okay. And then I'm going to give you an image that shows some samples generated using our acceleration trick. So from this image, you can see that our method can generate pretty diverse images that are like real-world images. And to give you more quantitative comparison, I'm also calculating what is the feed value. So here, so how you should be reading this plot is that here different subplots represent basically the same thing, but for different data sets. And for example, how you should be reading the first subplot is that if we want to, so if we run DDPM for NDDPM number of function evaluations, then the feed value we are going to get is roughly the same as running whatever acceleration method with an XL number of function evaluations. And also here, this red line represents our acceleration method. The blue line represents the acceleration method proposed by Li et al. And the gray line is basically the diagonal line, which represents the unaccelerated DDPM. So I guess from this plot, you can see that our acceleration method outperforms the unaccelerated DDPM and also the acceleration method proposed by Li et al. In all different settings considered here, suggesting that our method can behave well in practice. Okay, and just to summarize a bit the first part. So in this part, we propose a training-free acceleration method for diffusion model, and we obtain some proof guarantees for our method measured by the KL divergence between the output distribution and the target distribution. Our method is actually compatible with most of the diffusion model code bases, so it's very flexible. You can take any neural network from the existing diffusion model project. You can then apply our trick and then proceed to sampling. Okay, so I guess that concludes my first part. So maybe before I proceed, let me check. If we don't have any questions, so I can just proceed.
There is a question by Guanyang.
Oh, sure.
Yeah, a quick question. I wonder if the trick can be equally applied to generating higher resolution images, like CIFAR10 are relatively lower resolution, like for example, I don't know, 256 times 256, this quality of images.
Yeah, that's a great question. I guess here I present you two experiments. None of them are 256 times 256, but we are, okay, so actually we have completed one experiment that's on a data set 256 by 256. But we haven't like uploaded this experiment to the archive version. But the answer is yes, we are able to do 256 times 256.
And also, I'm curious on whether the scheduler plays a crucial role in either the implementation or the theoretical analysis. Because, for example, stable diffusion uses a different scheduler than DDPM.
Yeah, I think scheduling plays a very important role. Like for the theoretical analysis, we do have like a specific recommendation of the scheduler. Okay, so that's not like a specific choice, but it's like an assumption that that we suggest that the scheduler should follow. And for the experiment, we just follow the scheduler suggested or recommended by whatever paper that we are taking the diffusion model neural network from. Yeah, but the scheduling is like a very important thing. And if you look at like the previous papers, some of the papers, they propose to learn the optimal scheduler to enhance diffusion model efficiency. But here we are not learning it. Instead, we just like take the recommended scheduler from previous paper for the experiment part.
Thanks. And is it possible to, or have you already tested on, for example, the latent diffusion models? Like,
no, that's a good direction to proceed in the future.
thanks. Thanks a lot.
Thank you. Thank you for the question. Okay. All right. So there is no more question. I'm going to proceed to the rest of the presentation. So in the first part, we learned that diffusion model is a generative model. So it takes that input some noise, and then it passes noise through a bunch of denoising steps. And after all the denoising steps is completed, it outputs a sample that's hopefully coming from the target distribution. So a crucial component of this denoising step is the score function. And in the diffusion model context, we just learned this score function by training massive neural network, which is powerful, but on the other hand, is also computationally pretty expensive. Then a natural question to ask here is, suppose we, in addition, have access to additional structural information of the target distribution, can we utilize this structural information to design more efficient score estimation algorithm without involving the magic of deep learning? And this leads to the second part of the presentation. And in this part, I'm going to present you some posterior sampling algorithm that is built based on the structure of diffusion model. And this part is based on joint work with Andrea Montanari from Stanford. Okay, so let me start with this part with a short recap of the posterior sampling framework. So suppose we have a parameter theta, that is the parameter that we are interested in, and we impose a prior distribution pi on this parameter theta. And then we are going to model the observation D using a forward model P theta that's parameterized by theta. Okay, so with this D, our goal is to then to draw inference of theta based on D. For example, we might want to draw a sample from the posterior distribution of theta conditioning on D. So the posterior distribution, you can see that it's proportional to the product of the likelihood and the prior, but of course, usually we do not know how to compute the normalizing conflict. So sampling from this posterior distribution allows us to do many things like answering quantification, making probabilistic predictions, estimating intractable integrals, as well as performing Bayesian model averaging. So how to build a posterior sampler based on diffusion model? So recall that diffusion model handles arbitrary distribution mu, and it only has access to a bunch of IID samples D1 to Dn that's generated according to this distribution mu. So with this training data, we are going to then build a neural network to estimate that's intended to capture some properties of the target distribution. And using this neural network, we are going to build our diffusion model center. So this is powerful, but it's computationally also computationally very extensive, and it involves many GPU hours usually. But for the posterior sampling context, you can see that we naturally have access to the structure of the target distribution because it's a posterior distribution. And the hope is that maybe we can use this structure to build a score estimation procedure without involving deep learning. So I guess the idea is pretty natural, but the most important question is, of course, how to build this score estimator, and in what context can we build this score estimator? I guess it's hard to show that this sampling algorithm or this sampling framework work for every statistical model, but we have been able to answer this question in the conformative in the context of two statistical models, high-dimensional regression and the low-rank matrix estimation. So these, I guess, are two pretty fundamental models in statistics that has found a lot of applications. And for the interest of time, today I'm going to focus only on this low rank matrix estimation problem, and the other high dimensional regression case, the idea is very similar. So for the low rank matrix estimation part, I'm going to focus on this Spike-Wigner model. So under this model, we observe a symmetric matrix X that is the sum of a low rank component and a noise matrix. So here, this low rank component is beta over n theta theta transpose, and we denote the noise matrix by W. And this beta is a positive scalar, actually a non-negative scalar that represents the signal to noise ratio, and the theta is like a spiked component that we assume it follows an IID prior, product prior. And this W is a symmetric noise matrix. We assume that the off-diagonal entries of this W are IID coming from a normal 0, 1 over n distribution, and the diagonal entries of this W are IID from a normal 0, 2 over n. So this is like a pretty simple and fundamental model that's been studied by a lot of the previous papers. And our goal today is to draw a sample from the posterior distribution of theta conditioning observation X. So with this model assumption, we can actually write down the posterior distribution up to a normalizing constant. But once again, it's usually hard to evaluate the normalizing constant. So this distribution, if we look at it, then it's a distribution on Rn. And if we consider a large n, this is going to be a high dimensional distribution. And also for typical choice of the prior distribution, this posterior is going to contain a lot of nodes, suggesting that it's going to be a challenging distribution to sample for. And if we look at the previous algorithm that tackles distribution, MCMC algorithm that's been used a lot in the previous papers is the Gibbs sampling algorithm, also known as the global dynamics. So this algorithm performs very well, but if you look at the theoretical guarantee, then theoretical guarantee only works for beta that is less than a quarter. Which is oftentimes fall below the information theoretical threshold, and sampling in this context is no longer considered very interesting. And also, another popular class of methods that's been used a lot in the previous papers is the variational inference method. The variational inference method is also very good. It provides good approximation for the target posterior in many different contexts. However, variational methods do not directly lead to a posterior sampling algorithm. So the posterior sampling algorithm that we are going to introduce today is based on this stochastic localization process. And to tell you a little bit more about this process was first introduced by Ronan Eldon to establish connections between conjectures in probability theory. So to define this process is initialized at the origin and is defined through this stochastic differential equation. dyt is myt dt plus dbt. So here, this BD is a standard Brownian motion, and this MYT is the conditional expectation of theta conditionally on T theta plus relative T z equals y. And here, theta and z are independent random vectors with theta distributed according to the target distribution, and z is just like a standard Gaussian distribution. Okay, so I guess one property of this stochastic localization process is that if we look at this process yt over t as t goes to infinity, then this process also stabilizes to random points. And another property of this stochastic localization process is that for every positive t, if we look at the normalized Worcester distance between the target distribution and the distribution of this random vector mytt, then the square of this Worcester distance is going to be upper bounded by the inverse of t. And one implication we can get from this lemma is that if we want to build a sampling algorithm to sample from this target distribution mu, then it suffices to track this stochastic localization process until a very large t. And that's going to be how we build this posterior sampling algorithm. So before I proceed with the details of tracking this stochastic localization process, let me first establish some connections of this stochastic localization process with the diffusion models. So here I am putting both the stochastic localization process and the diffusion model reverse process. And one fact about these two processes is that these two processes are actually equivalent up to a change of time and a linear transformation. So if we are able to build a posterior sampling algorithm based on the stochastic localization process, then this is equivalent to saying, almost equivalent to saying that we can build a posterior sampling algorithm based on diffusion model, but with the denoising neural networks replaced by some more efficient algorithm to estimate the score function. Okay. So back to tracking this stochastic localization process. So first of all, this is like a continuous time process. So we have to apply appropriate discretization to approximate this process. And after that, I guess one very important component, as you can see, is we do not know what is this function MYT. So the big question is how to estimate this function MYT. So one observation under the spec model is that if we look at this MYT, then this MYT can actually be well approximated by M star, which is the minimizer of tap free energy functional FTAP. So this FTAP is indexed by YNT. So I guess in principle, the takeaway here is that if we want to estimate this MYT, then in principle, we can just solve this optimization problem just to find the global minimizer of this tap-free energy. But this problem is also highly non-trivial because if we look at this tap-free energy, then this is a non-convex function with potentially a massive amount of local minimum. So if you just run gradient descent or other simple algorithms, it's very likely that your algorithm is going to be trapped at one of the local minimum. And to solve this optimization problem, we are going to do the following. We are going to first show that although this function globally is not a convex function, but if you just look at the small neighborhood of this global minimizer M star, then we can show that this tap-free energy is going to be locally strongly convex in this small region. And then we are going to run approximate message passing algorithm. And we can show that after running this AMP algorithm for a sufficiently number of iterations, this algorithm is going to reach this small region where it is where the tap-free energy is locally strongly convex. Okay. And after that, we are just going to run gradient descent, which gives an accurate approximation to the global minimizer M star. So this entire procedure gives us an algorithm to estimate this denoising function MYT. And we are going to use that to construct our algorithm. And to tell you a little bit more about this approximate message passing algorithm, so this AMP algorithm is constructed using a scalar denoiser FC gamma. So this FC gamma is defined as the conditional expectation of theta conditioning on gamma theta plus square root of gamma g equals z. So here theta and g are two independent random vectors, independent random variables with theta distributed according to the target distribution, and g is just a standard Gaussian random variable. So to run this approximate message passing algorithm, we are going to first take a top eigenvector of this matrix X and denote it by mu, and we are going to normalize it such that the norm of this mu is going to be square root of n times beta squared minus 1. So AMP algorithm is just an iterative algorithm that's initialized at the top eigenvector. So basically, this iterative algorithm, you can just think of it as a combination of matrix multiplication and a nonlinear transformation based on this scalar denoiser. Okay, and of course, I haven't told you what are the constants here. We have like constants alpha tk and beta btk. So these constants alpha tk and btk, they are defined recursively, but they are just the functions of the prior distribution, the signal-to-noise ratio beta, and the time index t. So that's the approximate message passing algorithm. And to summarize a bit our posterior sampling algorithm for this model, we are going to track this stochastic localization process, and we are going to apply an appropriate discretization to track this process. And in addition, at every discretization time point, we are going to use the algorithm that we talked about earlier to estimate this denoising function and plug in this M hat to construct our posterior sampling algorithm. So this method also comes with theoretical guarantee in a region that's not covered by the previous algorithm. To be specific, let's look at this theorem. So if we denote by mu hat the output of our algorithm, and in addition, we are going to assume that the prior distribution pi is either discrete or has a density satisfying the log of this density. If you look at the second derivative, then the second derivative is uniformly upper bounded. So if either of these two conditions hold, then we can show that there exists two constants, beta L and beta U, with beta U strictly larger than beta L, that depend only on the prior distribution pi, such that if the signal to noise ratio beta is greater or equal to beta U, or it is smaller or equal to beta L, then under either of these two conditions, we can show that the Worcester distance between the target distribution and the output distribution, this is going to be very small. With high probability. Okay, so that's the theoretical guarantee. And finally, I'm going to conclude my talk with like a numerical experiment. So for this numerical experiment, I'm going to assume that the prior distribution pi is a uniform distribution over plus minus 1. So this problem is also called the C2 synchronization problem by using this prior distribution. And for the dimension of the problem, I'm going to take n to be 1,000, and I'll run our sampling algorithm to output theta alg. So this theta alg is an n-dimensional vector outputted by our sampling algorithm. Then I'm going to do the following. I'm going to take the first 10 coordinates of this theta alg, and also I'm going to take the first 10 coordinates of the true spike theta and denote them by these two notations. And then I'm going to take the inner product of these two first 10 coordinates. And because in this problem, we happen to know like what is the theoretical counterpart, mathematically, what is the true distribution of this inner product, we can actually compare the empirical distribution of this inner product we get through numerical experiments with the true theoretical counterpart. And this is the numerical outcome that we get. So here, different subplots correspond to different values of beta. And this orange line is the theoretical prediction obtained by mathematical theory. And this blue histogram is the empirical sample distribution we get using our experiments. So from these plots, you can see that these two components, they match pretty well, suggesting that our algorithm, at least partially suggesting that our algorithm is indeed sampling from the correct posterior distribution. All right, and to summarize a little bit the second part, so in this part, we propose a new posterior sampling framework that is based on the idea of diffusion model. As application, we can apply it in both the context of high-dimensional regression and low-rank matrix estimation. And for our algorithm, we derive Frugal guarantee in the previously uncovered region. Okay, so I guess that concludes my presentation. I guess we are 10 minutes early, so yeah, I can then take questions.